So moving upward in elevation, we wanted to look at how performance-based earthquake engineering and piers research has been applied to a number of engineered structures. And so we're going to do two aspects of this, one for bridge-like structures and one for building-like structures. And the first of those presentations will be by Marc Eberhard, who's a professor at the University of Washington in Seattle. Marc?
Thank you, Steve, and good afternoon. The tack I took for this presentation is one to, first of all, go back to the basics. I know that we're kind of talking to the choir sometimes, or preaching to the choir here, but a lot of people who, first of all, necessarily haven't drunk the Kool-Aid yet, or for all of us, I think it's good to go back and kind of remember why we're doing this. So what I really want to do is start off with the basics of what is our mission, how does it apply to transportation structures, and then go look at our program and see to what extent that it maps to that. And a good portion of this presentation is really to set up tomorrow. Tomorrow is about identifying research needs and where to go next. So what I really want to do is talk about our goals, talk about what we're doing. And I hope in your mind you're thinking, oh, that's good, but the next thing is something else. And that'll set us up for tomorrow. So going way back into our current mission, kind of go back to verse. Advance and apply performance-based earthquake engineering tools to meet the needs of various stakeholders. That's been our peer mission for a pretty long time. Now, what's the point of doing that? Why is performance-based earthquake engineering so important? Well, it provides some things that historically we haven't been able to do easily, either structural, geotechnical, or materials engineers. First of all, it's just a communication issue. It allows stakeholders to make informed decisions. You're not going to find many stakeholders who care about ductility factors, about any kind of engineering unit we care about. They may care about dollars. They may care about other aspects of performance. And so the first thing is just talking. That's an incredibly valuable tool that we bring to mind. The second thing, of course, is balancing competing objectives. It's never just about earthquake engineering. It's about all kinds of different factors you have to balance of how much do I want to spend, how much do I care about durability, how much do I care about all kinds of different issues. The triple integral and all the concepts that are involved in there allow you to provide weights to these various values. And even if your data is not perfect, even if your estimates have a lot of uncertainty in them, at least you can get a sense of the importance of these various factors, and you can put in your own weights as well. What's really important, of course, also is the variability in performance levels. Any kind of prescriptive code is great for many applications, but it turns out that for existing buildings, you may not want to do the same thing as for new buildings. For a nuclear power plant, you want to do something different than for a regular building. For a high-speed rail, you might want to do something else than for a standard highway overpass. And the last thing, of course, is if you try to do a new system, you either develop a new one or you want to evaluate a new system, you need to have some kind of common framework. And the framework has to be what's the performance. You can't just be comparing some of these engineering values we have before. And I'm sure you can think of a lot of other things, reasons we're doing it, but we always have to keep in mind this is the reason we're doing this. This is why stakeholders may care about the kind of tools that we're developing. Okay, so from a transportation system perspective, what are the objectives we're trying to satisfy? Spend a lot of time trying to figure out what value goes on what slide and whatever. I'm sure you can organize them different ways. This one works for me. The one, of course, is, first of all, is economics. Like you can argue everything's economics, but in this case, I'm talking about direct costs. That certainly includes construction, and depending on how charitable you are to the rest of our kind of traveling public, you could even add the costs of delays during construction, maybe noise disruption, things like that. But certainly construction costs. But if you follow through lifetime, a lot of money is spent on maintenance and inspection. That's a cost that, of course, goes through the whole lifetime of the bridge. If there's any problems, you have to repair it. In our kind of sustainable economy now, eventually you might even think about the eventual disposal cost. So all those things are certainly one issue which is going to drive every decision for any transportation system is a question of economics. Now, regardless of economics, you're never going to want to have something which is unsafe. I know we can't use the word safe because safe doesn't mean anything, blah, blah, fine. We really mean low likelihood of loss of life, very low likelihood of collapse. But in my discussions with owners, they really don't want the bridge to come down. That's pretty much the bottom line. And even though we don't talk about certainties, we want to be so far off on that curve of reliability that the chance of having collapse is almost zero. Now, more recently, we're talking more about disaster resilience. And of course, a bridge by itself isn't so important in terms of whether it functions for its own needs, but what matters, of course, is, as people spoke this morning, it's about the community. So a bridge is not only important because of its own value, but of course, in what roles it play. Do you have detours that bridge is out? Are emergency vehicles using that bridge? How many vehicles are using that bridge? How much is there a particular facility on one side of that bridge, like a hospital, that's needed more than anything else? And so having a bridge that's available either immediately after an earthquake or maybe in a few minutes, shortly after an earthquake, can be an incredibly important part of community resilience. And then part of also is that the whole issue of repair and inspection can itself be impediment to recovery. Even your bridge is fine, if it takes the inspectors and it takes the bridge agency quite a bit of time to go back and figure out whether it's okay or not, you can be down for a while. So not only does it have to be good, but also has to be apparently good, in the sense that people can realize that right off the bat. Because the bridge is closed, even though the bridge is safe, it's still closed. And the last one, which is really important to all kinds of owners, is a loss of revenue. Now, for some people, it might be tolls. For a port, that might be shipping that's coming in and might leave and never come back. For a train system, of course, it might be fares. Loss of ridership in the future because your railroad isn't available when they need it and they get out of the habit of using it. And all these aspects are important to the community and to the resilience of that after a disaster. A couple pictures up here, one of them showing a shift in the bridge on the left-hand side, the other one showing an offset where the bridge is in the straight. You can argue that those bridges are safe or unsafe. It doesn't matter. People won't be on that bridge after an earthquake. And then, of course, even more commonly now is a whole issue of sustainability. And that's linked certainly first to durability. Building bridges that don't last is going to be unsustainable by any measure you want to use. But beyond that, even for bridges which will have a pretty long lifetime, certainly the idea of embodied carbon is one which is getting more and more attention. And in that, you can imagine not only looking at construction, but the use of that bridge and eventually even the destruction of that bridge. But disruption to sustainability actually goes even beyond just the kind of carbon issue. Construction causes noise, that causes disruption to communities. You have traffic congestion, which of course has its own carbon kind of implications, has huge implications on the traveling public. And finally, I'm from Seattle. You can't have a talk about environment without talking about fish migration. And it may not seem like a big thing, but if you're trying to build a bridge across a river, and you really don't want to build it in the winter because it's cold, and so you mean you want to do it in the summer, that's exactly when the salmon are coming up the creek, it's a big issue for that contractor, it's a big issue for that owner. So you can imagine other kinds of environmental issues as well. Of course, for us, it's all about salmon. For your parts of the country, it might be trout or something else. But that actually has a big impact. Now, how are we doing? We mean us, but also, this whole performance-based earthquake engineering thing has certainly been the focus of PBEE. But as a group, we've been so successful, it's actually being used in many, many by other people as well. So I don't want to take credit for everything. I'd argue there's been an incredible soft implementation that is widespread through the entire community. We talk about performance in much different ways than we would have before PBEE began. Even when there's not a calculation that's different, the concepts are embedded in the discussions, not just in the firms that have the highest level of expertise and the bridge agencies that are the most attuned to research aspects. But any bridge office you walk into, any firm has a sense of performance as opposed to codes, talking to owners about these things. And certainly some major bridges, we've had some very explicit implementation of performance-based earthquake engineering. And then in education, which of course is how you affect things in the future, we have every year tons of students coming out who have these things embedded in their education, and then eventually, of course, they will transform practice as well. And even on the hard implementation, which is much harder, right? It's much harder to affect the AASHTO LRFD specifications because there's so much history built into that. But the whole notion of displacement-based design only makes sense if you're thinking in terms of performance-based earthquake engineering. So I'd argue, even though we're not the only one doing displacement-based design, that whole code, basically, that whole approach comes from these considerations. And then if you read the discussion in the various paragraphs and the commentary of the various codes, AASHTO for sure, Caltrans and some others as well, you talk about the way to discuss hazard, the way to discuss performance criteria. They're much more careful, they're much more explicit. If you go back and look at what was going on 20 years ago, 15 years ago, it was a much, much squishier kind of discussion. And then finally, even in some places, there's one code provision or another code provision which comes specifically from pier work, and one is about displacement capacity of RC columns. That turns out it's actually a national equation coming directly from a pier project. So of course, on soft, I think we've made transformative changes. On hard implementation, it's seeping into practice in many ways through works of pier and some others. Okay, so given that background, the Transportation System Research Program has sponsored a bunch of projects. And what I try to do is kind of organize those into two categories. I'll discuss a few of them just based because I had some nice slides on them. What I really want to do is get you thinking about, that's great, but what should we be doing next year and the year after that? Okay, so there's some work on ground motion selection. And I heard the first category here is really about, I'm calling it enabling technologies, overcoming implementation barriers and complexities. And Ross was so much better. He said moving performance-based earthquake engineering to practice. If I had seen his presentation, I would use that bullet instead of my long one. But exactly, it's used in test beds. It's used in research all the time. What do we need to do to be able to get it to the place where it's actually tractable, accessible, and the other things Ross talked about? So ground motion selection procedure, you heard about that earlier. That's about making things simpler. Stochastic modeling, bringing in uncertainties into the modeling of ground motions. What happens to long duration motions? We haven't considered that so far. And then even if you're using the same technology, can we develop tools which allow you to implement that technology without having to do all the work yourself? Even in my research, I need these tools because I don't want to become an expert in all those different areas. So there's several projects. One is OpenSea's tools for uncertainty analysis, a software platform for performance-based earthquake engineering that El Gamal and others are working on. The effect on size effects. And then finally, there's one test bed of, I just happened to mention there, the one of the Humboldt Bridge. Again, the test bed provides you the ability to go through all the procedure, see what takes a lot of time, see what's difficult, what needs to be filled in, and then what do we need to do to make this accessible to everyone. And then the second part of the research program has been really about developing these new systems and then getting better performance out of those systems. And there's a bunch of them you heard already about high performance fiber reinforced concrete. I won't talk about that again since it was covered this morning. Then a series of different systems, one on post-tension cast-in-place columns, dual shell columns, precast columns, rocking foundations, which is part of it was done by geotech side, part on the structure side, and then last one on bridge isolation. And these are all tools, at least most of those are all tools or different ways of building a bridge. And again, if you want to talk about which one is better or best for a particular situation, You can't do that without performance-based earthquake engineering. You have to be able to look at the entire life cycle of a bridge and see whether it's better using one approach or another, or maybe we're better off doing what we've always done. Okay. The projects are summarized on this website. If you just go to the pier website and click on transportation projects, you can see summaries of most of these projects which are up here. So for the next few minutes, you can just kind of look at what I'm doing as overview. There's a lot more details on that website, and I encourage you to look at it. So in terms of enabling technologies, where we talked about Jack Baker's work, which is just getting ground motions to a form where people like me can actually use them. Talked about using a stochastic approach analysis for spatially varying ground motions. So far, the methodology hasn't included that spatial variation. I love this slide because it's the most beautiful picture of a bridge I've ever seen. And it just shows that, of course, as we all know, due to wave passage effect, due to all kind of reflections, due to different soil conditions, you get different ground motion in different locations. How you take that into account. And the project looking at different methods. I'm just giving one particular result from it. We're looking at the difference between the nonlinear displacements at event compared to the linear ones, and comparing that for a coherent ground motion versus an incoherent ground motion. And what you might expect, as we're just showing here, is, of course, it makes a difference, and also makes a difference of what part of the bridge you're looking at, right? If you're at the end of the bridge or the middle, the effect of coherency will have some different effects. The one you heard about already was also the idea of bridge performance-based earthquake engineering program. It allows you to look at an ensemble of ground motions. It allows you to generate these finite element models automatically. Isn't that great? It then allows you to post-process all these things so that you actually get results quickly rather than having to write all your own scripts to look at what the results are. So a typical result is the one shown up here. On the x-axis, it shows the repair cost ratio. And then it shows the mean annual frequency, how often you're going to run into those costs. And it's done for a series of cases. That's a lot of work to get there. The good news is that there's actually a graphical interface which allows you to put in the data to get you to that result we just had. Doing it on your own is not so fun. Doing it with the interface helps quite a bit. Okay, another work here on the Humboldt Bridge is that test bed. We saw a slide similar to this before. That test bed is one example of applying it to a very complex system. A complex system that has all kinds of long spans, it has joints, it has a complicated soil profile. That's pretty much a whole enchilada. What we really want to do is say, if you apply it to what is one of the more complex systems, what do you run into? Well, certainly one of the things you run into is model complexity. The text up here is all a little bit small, but basically there's 10,889 nodes. A huge problem. It has, of course, issues for computational demands, which Frank will address for us. Thank you. But also the complexity of the data coming out, how you visualize it. And what's nice about this project is that it has structures, it has geotech, and it also runs, for even this complicated case, from the seismic demands, or kind of the ground motion on one end, all the way to costs on the other, for a pretty complex situation. And so, for example, it's looking at various kinds of failures. The pier can fail, the shear pier can fail, and of course, most drastically, a span can come unseated. And all those are built into it. And finally, you get the same slide that Ross had a few minutes ago, showing basically the effects of these various kinds of failures and the costs they have now as a function of the intensity of the ground motion. So you compare that, of course, with the ground motion intensity distribution. You can then also figure out this as a function of time. And you can see for low amounts, it's all about the piers and the shear key. But at the end, when you have the total collapse, that's, of course, when your costs become huge. Okay. The other aspects was developing new systems. There's a lot of ways to do new systems that work better. This is a kind of overview slide I stole from Steve, which looks on the left-hand side, talks about essentially hysteresis curves that go back through the origin with the hope that for a particular system, at the end of an earthquake, the structure will go back to where it started. And there's a lot of ways. If you look at 3 or 4 systems I'll look at, they all have that same characteristic. In some cases, it could be a rocking foundation. In other cases, some kind of pre-tension element or rubber band through it that just snaps it back in place. But in both those cases, you get this kind of center origin hysteresis curve. Or if you don't like dealing with all that deformation, you can also isolate the bridge, which is the last one I'll talk about. Okay, I'll go through these relatively quickly because of the time, but certainly the first work we've done was, done by Steve Main and his colleagues, was using a cast-in-place column with an unbonded tendon down the middle. And you can see the hysteresis curves in the bottom. In the red, it's that curve that goes back to the origin. In the yellow, it's classic reinforced concrete behavior. And as you'd expect at the end of an earthquake, the one with the red curve is much more likely to recenter than the one in the yellow curve. And if you actually look at the tests that were done, that's exactly what happened. If you go up even up to ductility ratios of 10, that's pretty high. Even in those cases, the displacement of the unbonded post-tension system was within 10% of the normal system. That's not a big difference. But the main thing is, even at those very large displacements, the residual displacements, displacements at the end of the earthquake, were less than 0.6%, which was about 6% of the total displacement in the bridge. So that showed the success of that technology. Now, other people have come afterwards and have systems which also have that post-tensioning. In this case, it's work done at San Diego by Jose Restrepo and his colleagues. This is a system which also has the advantage of accelerated bridge construction. If we're worried about disruption to traffic when you're building things, you really want to put things up quickly. And also has the advantage of being resilient, of having a self-centering behavior and coming back in place, and also even has the advantage of having some a little lighter than some other systems. And just to describe it quickly, it's basically 2 sets of steel shells, an outer one and an inner one, with a grout in between those 2. And then down the middle, there's PT bars that provide you a recentering force. And then to dissipate energy at both the top and the bottom, there's energy dissipators can take different forms depending on which variation you're looking at. The idea here is you now separated the column stiffness from the energy dissipation. And the idea is also that at the end of an earthquake, if you want to, you can certainly inspect those. And if you want to, you might even be able to replace some of those components and get back to business. It has less structural damage than monolithic systems, small residual displacement. It's very resilient, operable after a strong earthquake. And again, that energy dissipation is a separate component which you can take out and put back in. And as those hysteresis curves show on the bottom, the one on the left is kind of classic reinforced concrete behavior. Those little red circles show that for zero force, you cross at large displacements. And then for the right-hand side, the hysteresis curve shows that green circle shows that you're always going back to the origin. It's actually from walls, but it's really the same concept. The one we're doing at the University of Washington has a lot of similarities. We're essentially doing a pre-tensioned version of that. So the column is made in a precast plant with pre-tensioning, not post-tensioning. It's brought out to the field in that the manner that you put the column actually just in the middle of the footing with the steel there. You cast the concrete after the column is there. You bring in a precast column on top, and then you put it through those holes in there to allow you to engage the column bars, and then you go on with the rest of your bridge. And we've done a bunch of different tests, capping the column connections. We've done both for reinforced concrete, classic ones, a precast version, and a pretension version. We'll also make those same connections for precast column connections to footings. And then we also did some tests between precast columns to drill shafts, which is, of course, a real common way of doing it. And the next step is going to be to incorporate these new materials that you heard about earlier today from Claudia, to say, can I not only have the precast advantages and the pretensioning advantages, but can also have the increased displacement capacity by having the improved materials. The next step is yet another way to get recentering, which is to have rocking behavior. So in this case, heard about before, it goes up, it comes back. It's quite interesting. And within this project is very much related to the one that Ross spoke about. That's great, but what happens in the rest of the bridge? And so one case, a fixed space pier, where the deformations are taken more or less at the base of that column, versus either a shallow foundation or a deep foundation that's rocking, we just allow that foundation to go up and down. And again, what's nice about performance-based earthquake engineering is that if you follow through all the steps, which they did, by the time you're all done, you can get this kind of result. And I've skipped through a bunch of slides. On the vertical column, there's total repair cost. On the right-hand side, there's the spectral acceleration at 1 second. And you can see essentially that for low ground, or for up to about 0.5 or so, it doesn't make much difference which system you use. But as you get to very high levels of acceleration, the rocking system is going back and forth and the cost doesn't really increase. For the cast-in-place column that's fixed, you're getting more and more damage at the base of the column, so your repair costs go up. So the red line that is the fixed base, most of that damage is coming from damage at the base of the column. And then the blue and green lines are spread footings and pile caps where you've allowed the system to rock. So what I'd argue again about performance-based earthquake engineering is you can actually have that discussion. Without all these tools, you can't even have the discussion of which system is better. And then the final example I want to use is one of the isolation of segmental bridges. You can isolate a bridge by itself. If it's continuous, that's great. If you have a bunch of segments, there's no thing telling you those segments all have to go together. In fact, they're not likely to go together. So on one hand, they bang together, which is shown on the left-hand side. On the other hand, at the end of the earthquake in particular, you can have this big offset at the end, which is not going to make your owner very happy, particularly if it's a rail line, for example, and you want to have that alignment at the end. And so in this project, it's looking at the effect of having some guides, which essentially restrain the relative motion between the segments. It's kind of a stopper in one direction. In the other direction, it keeps them close together. And the idea in this motion is that as the bridge goes back and forth, you allow some relative motion, but only a certain amount, and that's restrained by these lockup guides. And so a quick example here of what a lockup guide might look like. You can see at the top, you see how it deforms when it moves sideways, and it also has longitudinal constraints for a certain amount of motion. And then finally, unfortunately, Steve already showed a picture like that. He had people in his. It was tested not only for the bridge by itself, but the bridge with the rail on top. And certainly, if you're in the rail business, you want to know to what extent that rail is going to help keep things together. Okay, so the idea here was to give the basis for performance-based earthquake engineering. Why are we here? What are the disadvantages? Remind ourselves of the whole bit. I've argued that it's transformed bridge engineering culture already. That's also in the process of transforming standard practice through education, through little code provisions, through major bridges. We're going in that direction. We have to figure out how to implement it. We have to figure out what level of complexity is appropriate for different circumstances. But I think it's coming, and I think it is affecting change, is bringing about change. The Transportation System Research Program has basically focused so far or lately on enabling technologies, or as Ross would say, moving performance-based earthquake engineering to practice, and also in developing and evaluating new systems. And so please think and come tomorrow and participate in all the various sessions. We not only want to talk to you, but we very much want to listen from you, to you as well, because the information from tomorrow's sections, both in the morning and afternoon, will be used to guide the next phase of PIER. Thank you very much.
Thanks, Mark.